presenting to us. And we are proceeding now to the competing technology, superconducting quantum computing. This is presented by Stefan Filipp. Stefan was a member of the Wallraff group at the Quantum Device Lab of ETH Zurich from 2008 to 2014. There he was working on cavity QED systems, doing quantum optics and information processing with superconducting circuits. Then in 2014, he joined IBM Thomas J. Watson Research Center in New York, and later on in 2015, he moved to the Zurich lab, where he became a technical leader of the superconducting qubit team. And since May 2020, we are very happy to have Stefan here in Munich. He started as a full professor at Technical University and is also director at the Walter Meissner Institute. And today he will talk on tailored quantum gates for chemistry calculations on superconducting quantum devices. Stefan, please go ahead, unmute yourself and share the screen with us.
So thanks a lot, Rudolf. Thanks a lot for this kind introduction. So now you should see my screen.
Yeah, perfect.
Perfect.
So
yes, so I'm happy to give my first talk as a member of the Walter Meissner Institute at the Bavarian Academy of Sciences in the Garching area. And so the topic of my talk will be about quantum chemistry and doing calculations on that with superconducting qubit devices. And so within this talk, I'm still wearing my IBM hat. So all of these experiments have been carried out at IBM Research in Zurich. But as Rudolf mentioned, I'm now sitting in Garching, and I'm very happy to continue these efforts or related efforts here in this area. And so I'm excited to be part of this conference and this virtual experience. So I will talk about experiments on a different platform here, but let me just remind me a little bit what the status of quantum computing is and why we are doing this. Because it's going in a slightly different direction than in the logical qubit and error correction context. We all know that quantum computing is, from the scientific perspective, extremely interesting because it can solve us problems that are too complex for a classic computing system. And I guess everybody of you knows about all these different challenges that could potentially be solved, be it factoring or solving systems of equations in algebraic algorithms, or doing combinatorial optimization. And the one that I find the most intriguing also for doing something right now, and where we can see the first effects already and the first scientific results, is the simulating of quantum mechanics. And doing it in a digital basis or in an analog basis, but at least tackling a quantum system that is described by quantum mechanics itself, and using a man-made system to do some computations on that system. So focusing on simulating of quantum mechanics in this chemistry context will be the topic of the talk. Where are we? Thomas has already alluded to the state of the art that we are having right now. We have several systems that we can think of as a viable solution for building this quantum computer. We have superconducting qubit systems, we have ion computers, we have several others, but probably these are the first now that are already, so to say, on the market, that one can use, that everybody can use, and scientists can use, and show already that there is some quantumness in the systems that you can use and exploit. There's also systems in development. There's European efforts, there's other efforts, hopefully also at some point Bavarian efforts. And we all know that there's many challenges ahead, being it in the scaling context, but also coherence. We are always limited by coherence. There is not enough coherence available. It can always be more. But also what we saw, control errors, like non-local errors, global errors, errors in the lasers or in the microwaves, etc. But still, we have already these first signatures of quantum advantage. That is demonstrated. We can debate, and depending on which hat are where, there will be more or less debate on that. But there is at least the first signatures in this direction, and so we're going in the right direction. But the next milestone, and that's also probably under debate, what is actually the relevant next milestone, is finding a practical quantum algorithm that really gives us some results that we couldn't get otherwise, that is also useful. And the other thing that was Thomas mentioned, building a logical qubit or building two logical qubits and going to this universal quantum computer that can solve us all of these nice problems that I had on the first slide. So I will focus more on these practical quantum algorithms, not going towards the logical qubits, and see what are the ways to improve the system to finally get there. And one of these applications that one could have in mind is about interacting fermions. So it's basically at the core of most of the challenges in computational physics and high HPC in high performance computing. Solving this electron configuration Hamiltonian, where we have some potential energy, we have the interaction energy of these electrons here, and solving this Hamiltonian in the sense of calculating its properties like ground states or reaction rates, or its molecular structure in terms of what are the excited states. That's a difficult problem where a classic computer typically fails if the molecules get too complex. And why is that? It's just because Hilbert space is too large. And that's this nice table that one can put in just counting how much information would be needed if you would like to store a quantum state. And we can start with a single qubit. We have two coefficients that describes this qubit state, two coefficients. Say we have 16 bytes. If we have two qubits, we have 2 to the 2 coefficients, we have 32 bytes. Then we can just go on and think about what would it need to store the information at 32 qubit state. That already gives us 32 gigabytes. That's still doable. But for 64 already, we reach the information that's stored in the internet. It's 128 exabytes. And that's already something that cannot be easily, that's not easily available. So, and then we also see this boundary that's typically quoted. Between 32 and 64, it's typically 50, 54 qubits or so. It all gets extremely challenging, and adding a few more qubits, it gets unsolvable for a classical computer. So if we have a molecule that is described by, say, some 50 electrons, 60 electrons, it is kind of obvious that even for storing this waveform in a classical computer is kind of impossible, or extremely challenging. One should also say that that's not the end of the story for classical computation. There is clever scientists, clever researchers who came up with extremely many approximation methods that work, and that work pretty well. And so it's not that we're comparing to this brute force method. We can just see that using different methods, we can approximate, for example, the accuracy of finding the ground state of a molecule quite well. There is methods like Hartree-Fock methods, where we have some mean field theory, and we are basically dealing with a single particle in a mean field. That scales with n to the 3. So that scales with n cubed. N is the number of electrons. So that's pretty relaxed scaling. But it's also not very accurate. We can go to the other side of this graph and look at some coupled cluster methods. They scale already with n to the 8. So that's a high order polynomial. So that scale is quite unfavorable for implementing or doing some computation, but we get larger accuracy. And there's also DFT methods which are pretty poor in accuracy, but pretty easily to scale. So we just have to keep this in mind, that we are also trying to merge this graph merge different methods with quantum computer, so that we can benefit what classically what researchers found already in classical theories and computation theories. So to solve this, we use superconducting qubit systems. I don't want to say too much about the comparison with trapped ions, but they're a nice system which we can use for scaling up to the number of that we have seen before, at least to the 50 qubits, and probably even more. Just as a few numbers to mention, we have relatively long lifetimes, meaning 100 microsecond lifetimes or so. We have gate times that are in the 10 to the 500 nanoseconds. gate times, and that gives us typically gate errors of 1% or so. We have transmon type qubits. That means our qubits, that we have also seen before, consists of not two states, but of more states. So there is leakage, but we can single out these lowest two lying states as our qubit states. The typical frequencies are 5 gigahertz, so that's in the microwave range. And that also means that we can use microwaves as communicating elements between these qubits. And that's done with these microwave resonators. So if you look here on this graph here, you see the qubits, and then you see these wiggled lines. And these wiggled lines are basically BNC cables, so coaxial cables. And these are used for transmission of photons, or basically to couple these qubits on the chip. They're also used for readout, and they're also used for noise filters. But basically on the chip, they have the function of providing a way to let the qubits interact. We have a slightly different tweak. We use tunable resonators. We use a different element here, which resembles more a qubit than a resonator. And we will see with this one, we can actually get to gates which are helpful if you think about getting to a practical algorithm at some point, because they will be useful in matching the theory, matching the task to do on the hardware. So what is the system that we are using? Since we are dealing with systems in the microwave range, that means we have to care about heat and radiation. We are also dealing with superconducting systems, so that means we have to go to low temperatures. And that means typically we are around 15 millikelvin. We're using so-called dilution refrigerators to cool these chips down at the bottom of this stage. Here you see the interior of a dilution refrigerator at the different temperature stages. It's basically like a multi-layer thermoscan with different layers having different temperatures. That's all for providing shielding against noise and radiation. And for control, we use microwave electronics. The picture you see here is still an old style picture for an experimental setup as the one that we are using. Modern systems, and is also a more integrated microwave electronic stack where you can do this in a more modular fashion. Where are we right now? So as I've said, I'm wearing the IBM hat. So from IBM side, we have several qubits available that can be used for research and that are also online available. But the point is here that we can build systems that can host up to 50 and a little bit more qubits. And they are coming in this integrated fashion. And with these qubits, you can then use and run algorithms on that. In Zurich, we did a little bit different direction. Our research direction was actually to figure out, can we use different elements and have more adapted gates that we can use for implementing specific algorithms. So we're using a tunable coupler gate here, for example. And this gives us a different gate set that we can then use in our experiment. So let me say a little bit what is the properties of this tunable coupler and what gates we can do and how good are these gates. So for this tunable coupler, we have these two qubits here. We have this element in between, and this element in between can be thought of as another qubit. It's just a qubit that is tunable in frequency, and this qubit provides interactions between qubit 1 and qubit 2. And it does so by modulating of this coupling, this J of T, and we can modulate this coupling by sending in a current that changes the frequency of this element here. So we are modulating the squid loop inductance via an external flux, so that's at the physical level. At the more conceptual level, we are modulating the detuning of the qubits to the coupler, that's this delta, and this gives us in our Hamiltonian an effective qubit-qubit coupler. So how can we use this? We can use this to mediate, for example, an exchange type interaction. So this 1, 0 means that the first qubit is in the excited state, 0, 1 means the second qubit is in the excited state. So if you modulate this coupling now at a difference frequency, so to say we are providing energy to enable this transition here, we don't have to move the qubits around, but we just enable this transition by modulating the coupler at the right frequency. And what we get is an exchange type interaction. We can modulate also not at the difference frequency between the qubits, but at the difference between the 2 qubits in the excited state, the 1, 1 state, and the 1 qubit in the second excited state. So that means we are leaving on purpose our computational subspace, but we return to the 1, 1 state. And what we get is that the 1, 1 state picks up a phase. And that's also quite useful because with this we can actually implement the controlled phase interaction in our system. So we have heard that having good control over the gates can be also helpful in digital analog computation. So what we have done here, we implemented and demonstrated that we can actually tune this gate in amplitude and in phase, meaning that we can implement not only an I swap or a square root I swap gate for a complete swap of the interaction, but we can tune this by tuning this theta and by tuning this phase here. So what we get here is the fidelity as a function of this theta value, and the theta is basically how long or at what amplitude we are operating this gate. And we're getting a 95% fidelity in this case, slightly decreasing because the length of the gate changes actually. We can also control the phase of the gate by controlling the phase of the pulse here. So that's given by how good what we can do at the pulse level is reflected in this phase of the gate. And also here for different phases, we get this 95% fidelity. So we have good control. The numbers could be better in recent experiment, but we can see that we have good control over both of these analog parameters in the gate. So we can create arbitrary 1, 0, 0, 1 rotation. How do we then characterize this gate? So a typical way how to characterize quantum gates is by using randomized benchmarking sequences. So basically we're doing a randomized sequence of gates, and at the end we do an inverting unitary so that all these gates here are basically proportional to the identity gate. And then we measure 1 qubit. What we would find is that the population is always 0, but with the number of Clifford gates, with the number of gates, we are approaching 0.5, basically reflecting that we have a complete mixed state. And from this, we can extract now the error that we would get for a single gate, and that's about 1.4% in this case, with a gate duration of 117 nanoseconds. We can characterize also the CZ interaction. So going from this 1, 1 state to the 2, 0 state and back again. What this does is actually, if you look here, we are starting in the 1, 1 state. We go to the 2, 0 state, we get a component of the 2, 0 state and return again. So this encloses, as shown on the log sphere, a solid angle, and this gives a geometric phase. So that's a nice way to depict this gate. And if we now change the delta, the tuning and the amplitude of the gate, we can actually adjust the solid angle and we can adjust the phase. So we can adjust a sigma C gate here. That's basically the phase that is picked up by the 1, 1 state. We have this formula for this solid angle. And we can do a control Z gate if we choose the solid angle accordingly, so that we get a pi phase. We can now go ahead and characterize both of these gates, and that's actually interesting because we have now a second gate available that we can readily use in our algorithms. We have the CZ gate, which is, and we have identified some of the reasons why this is the case, a little bit better in performance. We get a 0.9% error per gate. The limit is also, we have identified that as timing errors. So we have to return to the 1, 1 state. to avoid leakage. And we can characterize this as a function of gate time. In comparison to the I-swap gate, we see that the I-swap gate is performing a little bit worse than the CZ gate, and also it has much larger spread. And that's actually caused by that the I-swap gate is limited by controlled phase, so correlated errors. That's what we nicely see. So this exercise is basically so that we can go on now and use this I-swap gate, because that's useful for quantum chemistry. So what do we want to do to calculate the properties in the context of quantum chemistry? We want to find the ground state of a given Hamiltonian, this electron configuration Hamiltonian. We want to minimize this energy function, the cost function, which is the expectation value of this Hamiltonian. So first, we have to go from this Hamiltonian problem, we have to map it into qubits. There is known procedures for that. That's Hamiltonian for the hydrogen molecule. We then prepare trial states. So these states here, we prepare them by choosing certain values of these parameters. We evaluate this cost function. And if we have evaluated this cost function, we optimize over these theta values. So send it back and forth between a classical and a quantum computer. And if these theta values are chosen properly, then this trial state gives us the minimum of this cost function, and we find the ground state and the ground state energy of the Hamiltonian. So this gives us the solution. Another point is, we can just go ahead, and as Christian Mendel showed yesterday, we can just go ahead and prepare a state by using some entangler. So we have some qubit register, we do some single qubit gates, we do entangling gates, and we navigate in Hilbert space and optimize over these theta parameters. Then we measure the energy, and for the hydrogen molecule, we have to measure these Pauli strings to get to the final energy value. We note here that the target state that we're preparing, that's not specific to a chemistry problem, that's some state. So we're basically exploring the complete Hilbert space. And with this, we've also seen this yesterday, these curves we get for different molecules, we get nice ground state curves as a function of the binding energy, as the function of the distance between these molecules. We see that they are not perfect. We see that for the H2 molecule, it kind of works, but for larger molecules, we get lots of discrepancy between the theory prediction, this dashed curve, and the experimental data, which is this black points here. So the question is, can we improve on that? So one way to improve this is to use different schemes for error mitigation. So that's not to be confused with error correction, because we don't do a full error correction scheme here, but we just use a method so that we can extrapolate on the errors that have occurred. So one way to do this is what is known as Richardson extrapolation. So we basically know that under some convenient assumptions on the noise part, so that it's well behaved and has a flat frequency spectrum, we can just extend the length of the gates for this entangler. So what we would assume is that just proportional to the length of the gate, more error is picked up. So we have now a scaling parameter, this C2, and we can do the same algorithm for different scaling parameters, so for different lengths of the gates, so these C2s here. So if we have recorded the expectation values, the cost function of interest for these different scaling factors, then we can extrapolate to zero noise. The zero noise, denoted here by this E star, would give us the proper value of, in this case, the ground state energy of our of the wanted molecule. And this works pretty decently. So in this graph, for example, for the hydrogen molecule, you see that for different stretch factors, the C's, we more and more approach the ground state value. And when extrapolated, we are almost perfectly aligned with the theory curve. There is also other mitigation strategies, like using symmetries of the system. And for example, there was a recent publication also by Google on that uses also different methods. But we can also be a little bit more careful, and that's what we had in mind, by selecting what states we use as trial states initially. So then we have to go back a little bit and think about what is the basis states that should be used, and how is this reflected in the preparation of the trial states. So for example, if you have this hydrogen molecule, there is 2 protons and there is an electron wave function, where the electron either is even, so the gerade wave function, so it's symmetric, either left or right, and has spin up. Or it's symmetric and has spin down, or it is antisymmetric, so it's the ungerade wave function. So the wave functions around the nuclei have different signs, with spin up and spin down. So basically there's 4 different wave functions to describe this hydrogen molecule that we can use. The relevant subspace is now 2 electrons, so we have 1 and 1 spread out over all these different basis functions here. And that's basically already 1 subspace that we are using. And then we can also see that we have now 1s and 1s, so we have always 2 1s, so we have always 2 electrons in here, and that already tells us what is the right ground state, what is the ground state that we are searching for. We are searching for a ground state that is a superposition of these states, where the 1s are basically distributed over the 4 basis states. And that gives us a type of gate which is natural to the system, which is the exchange type gate. So we just need to exchange these ones. So if we have a gate that actually does this also in hardware, then we stay within this subspace where the ground state has to lie in. We can also map it to 2 qubits by neglect the zero magnetic moment subspace, and then we will perform the experiment on the 0-1 subspace. With 0-1, so with 2 qubits. We did also an analysis before, what would this mean for larger molecules. So if we just go ahead and do straightforward the variational form I showed before, we would immediately reach the T1 boundaries and have too many gates available. If we look at problem-specific trial states where we use exchange type gates, but encode them in C0 gates, we would already lower this limit here significantly. And if we will have a direct implementation in hardware, we could go actually with much less gates. Sorry, my computer is a little bit slowing down. So that's what we did in experiment with 2 qubits. So we want to find out the ground state of this Hamiltonian. We do a variational algorithm where we prepare 1 qubit in the 1 state, so we have 1 excitation there. We do an exchange type interaction, and then we measure the Pauli matrices that are of relevance. So we are navigating only in the relevant ground state manifold, and see that we are getting close to what's known as chemical accuracy as a function of bond length here for the ground state. And that's basically shows that we can use this method because we are not navigating the full complete Hilbert space, but we are staying in the relevant subspace. We did a little bit more on that, but just briefly, we can also use this method for calculating excited states. It works on a similar basis. We just have to know basically what is the difference energy between the zeros, the ground state, and then a higher excited state. We can decompose this into Pauli strings. So we measure not only the Pauli strings for the ground state, but also other Pauli strings. And from these measurements, we can actually also calculate not only the ground, but also higher lying excited states with a similar chemical accuracy. So that tells us that we should actually use our knowledge, our prior knowledge in how to navigate Hilbert space. We should use hardware that is adapted. We should use trial states that is adapted to our problem at hand if we know what to use, and so that we can scale this up. So as an outlook, what we are interested in is scaling this up, going towards higher fidelity gates. We're also looking into multi-qubit tunable coupler architectures where we get more connectivity. So that's still a problem that we have limited connectivity and we want to explore Hilbert space faster. So that's one of the research directions. And with this, I want to thank the team at IBM Research Zurich that did the experiments, our theory collaborators, but also our university collaborators and the team in research, at IBM Research in Yorktown. If you're interested, then please send me a note. We're looking for skilled people. And with this, I want to finish with stating once more the goal of a quantum computer, building a computer that's based on quantum physics to solve a problem that are otherwise intractable. And to reach this goal, it will take us a while, but it's a so interesting goal that I hope that we can reach it in the near future. So thanks a lot for your attention.
Yeah, thank you, Stefan, for the presentation. And I'm handing over to Stefan, who hopefully has many questions for your talk.
Okay, so I think I have to start again with a question myself, because so far there are no questions from the audience. But again, I encourage everybody to submit questions. Actually, on passing, you said, I think it was for your CZ gate, that you had below 1% error, but and you could identify this timing problems or issues.
Sorry, you got a little bit interrupted. We could identify what was the reason.
To be identified?
Yes, so in this case, it is that we have still some leakage. The coupler is actually another quantum system, and we are leaking out of our computational subspace into the coupler. So we have to basically apply some more clever pulse shaping to get rid of this and to eliminate this. And then we, hopefully in the next step, we can get to even lower gate errors, also for the CZ gate.
Okay. So since there are still no more questions or no questions from the audience, again, let's hope for them. I have a question. So we mentioned that that one approach is in Zurich to go to even higher fidelity gates. So in what sense does quantum control play a role there, or an optical control theory?
So that's what we are exploring right now is first going this direction and increasing the coherence is one way, and the other way is going towards this short gate limit where one is easily limited by leakage into other levels, and that's one of the problems with superconducting qubits. So having here control schemes that avoids these other levels, that's one way to go. But it's also, we are seeing that adapting these control methods to the system is also challenging from the control, from the hardware point of view. It's not only the quantum hardware, the chip itself, but also the control hardware is needed that runs optimization schemes in a closed loop scheme and that are fast enough for actually characterizing and calibrating the system and calibrating the pulses in an efficient way. And while this is the question that is basically how can you do this not only for a single qubit but 2 qubits, but then also for a full chip with having to take into account correlations between many qubits at all. So, but that's one route forward to get to faster and also higher fidelity gates.
Okay, I still don't have any questions from the audience. I would suggest to, if more questions come up from the audience, to discuss that during the roundtable discussion and hand back to Rudolf.
Yeah, I would like to encourage everybody to raise questions already during the talk. You can send the question to the webinar chat, and Stefan is collecting the question and presenting this question to the presenter. We have now a round table discussion with Thomas and Stefan in round table room C, and we reconvene to this session at 4 o'clock exactly.